Our topic here is vector fields. And first of all, what is a vector field? A vector field on a domain or in space is a function that assigns a vector to each point in the domain. A field of two-dimensional vectors would look like this. Vector field f equals some function m of xy times I plus some function n of xy times j. That's a two-dimensional vector field. A field of three-dimensional vectors would look like this. Vector field f is m a function of three variables times I plus n a function of three variables times j plus p a function of three variables times k. So here's an example, pretty simple example. One, if we could imagine attaching a projectile's velocity vector at each point in its trajectory in the plane of motion, then we have a 2D vector field defined on the trajectory as shown. This isn't a perfect picture, but you imagine if this is the velocity vector, think about this thing, it's a little faster at the bottom. As it gets closer to the top, the vectors would be getting a little shorter. That means it's slowing down a little bit, and as we come back down again, it gets faster again towards the bottom. This picture might not be perfect, but I think it does illustrate that at every point in the projectile's path, there's a vector that would represent its velocity at that particular instant. If you can imagine a gradient vector at each point on the surface of a function of two variables, then we have a 3D vector field on that level, on that surface. Sorry, that's not level surface, on that surface. So in other words, we've got a surface, a function of two variables, and we have a 3D vector field because at each point in that, on that surface, there is a gradient vector, and it would be pointing in the direction of steepest ascent. So naturally, a gradient at each point of all the level curves creates a 2D vector field, right? Because the level curves are all inside the xy plane. So, velocity fields describe the motion of a particle in the plane or space. An example would be velocity vectors determined by a rotating disk, like a CD or a wheel or a tire or something like that. Further from the center, the longer the velocity vector is, right? Because at the center, the rotation isn't as fast as it is on the outside. Ride a merry-go-round and you'll understand. So this would be, I only drew, let me see, I guess 12 vectors in this picture, but there are vectors at every single point in this picture of this spinning, rotating wheel. As you can see on the rim, the velocity vectors are longer than they are towards the inside. Actually, right here, the velocity vector would be of length 0 at the origin because there's no velocity there. It just keeps spinning, but it's not going anywhere. Another example of a vector field would be gravitational field. Newton's law states that particles attract each other based on their distance from each other and their mass. Actually, based on the square of their distance from each other and their mass. But the formula for the attraction exerted on a particle of mass m at the point xyz by a particle of mass m2 located at the origin is, notice this is the square of the distance from xyz to the origin. So it's inversely proportional to the square of the distance and proportional to the product of the masses and the gravitational pull and a unit vector, right? Where it's a unit vector and points from the origin to the point xyz. In this drawing, I put the vectors in here representing gravity pulling towards the Earth's center at the origin. This is kind of what it would look like. If this is the Earth, then the further out you go, gravity is smaller. But the closer to the center of the Earth, gravity is larger. So the vectors closer to the Earth are longer than the vectors that are further away. And similarly, electric force fields, Coulomb's law is almost the same law. The charged particles attract each other in amounts based on their distances from each other, actually the square of their distance from each other, and the amount of charge. See, here's the square of the distance from each other, the length of the vector r in the square, and then the q1 is a q2 are charges on the particle, c is a constant, and u is a unit vector that points from one to the other. That's a description. There are many, many vector fields. I guess examples I gave you, gradient on a surface, gravity, the vectors on a velocity vector on a spinning disk, etc., even velocity vectors on a tossed object. Those are all examples of vector fields.